we've seen sort of compositionality of programming languages, where terms are made up from subterms, and maybe semantics are defined by induction on this subterm structure. So we've seen this in Gordon's talk, Christine's talk, many talks. Okay, and then there's the other kind of compositionality that we've seen, mostly, for example, from people who work in string diagrams and categorical quantum mechanics. David Spivak's talk was full of stuff like that. So was Jamie's and John's and Brendan's and Ross's and a lot of people. So we've seen two different kinds of compositionality. They have some things in common, but they're still somewhat different. And what I will tell you about is sort of one attempt to marry these two worlds actually together. So 5 years ago, I was part of a big project for the US government, and we were developing a quantum programming language. The purpose was not to actually program a quantum computer, because they don't actually have one, we think. But of course, if they did, it would be classified. But as I understand it, the main purpose was to do resource estimates. So implement some actual quantum algorithms from the literature, and then figure out what powers of 10, like how many gates or resources these algorithms would actually consume. So as part of this project, we developed the quantum programming language Quipper, which I will talk more about. And we also had to, it was sort of a given sort of goal of the project to implement 7 quantum algorithms that they specified. Okay, so they were not trivial algorithms like teleportation, but they were really complicated algorithms like estimating the ground state of some molecule or playing the game of hex. One of the algorithms played the game of hex, was a winning strategy for hex, and it's faster than the classical algorithm. And one of them was solving a linear system of equations, which everyone thinks is easy until they're exponentially many equations in exponentially many variables. Then again, it's something you can do on a quantum computer faster. And there were several other things like walking around quantum random walks on a graph and things like that. So this language that we implemented is scalable in the sense that we have generated quantum circuits with, I think some of the largest ones was 30 trillion gates. Okay, so these, it's quite scalable compared to, say, if you do teleportation, all right, which has like 5 gates. One of the algorithms dealt with doing some computations in number theory, actually computing the class number of some kind of ring, okay? And to do that sort of thing, you need to manipulate sort of in a quantum way quite complicated data structures, like data structures, for example, representing an ideal in a ring, okay? So we have, in Quipper, we have quantum data types, similar to sort of data types in a usual programming language. And among these types, of course, were things like lists and trees, but also more complicated types. And we actually have a whole fixed point real number computation. We implemented fixed point real numbers with functions like plus and times and sine and cosine and the hyperbolic cosine and so on, all in sort of this quantum setting. So it's quite scalable and big. And it's higher order, so you have functions inputting other functions. This often happens when some circuit is depending, for example, on a family of oracles or something like that. And we had to do this very quickly, so Quipper was actually originally sort of designed in about 6 months. And to implement all 7 algorithms took another year after that. And in order to be able to do it fast, we embedded the whole language in Haskell, which is an existing functional programming language. And when you write an embedded language, you can basically do it very fast, because you don't have to write a new compiler, a new type checker, a new anything. Just use the infrastructure of the existing programming language. And one of the disadvantages of being embedded in Haskell is that the language didn't end up being completely type safe. Okay, Haskell has many wonderful features, but one thing it doesn't have is linear types, and another thing it doesn't have is dependent types. And if you don't have those two things, it's not going to be completely type safe for a quantum language. So let me actually show you Quipper for a second here. I could probably spend the rest of the I could spend all the time just demoing Quipper because it has many interesting features, but I just want to give you very quickly a flavor, okay? So here's a very simple Quipper program. for constructing a circuit that takes the Boolean AND, of a bunch of bits. It's written as qubits here, but these are actually classical gates. They're all in the classical basis. So if you want to AND together 2 bits and output another bit, then what you do is you generate a third bit, initialize it to false, and then you do a controlled NOT gate, which will negate the third bit if and only if the first 2 are both equal. If and only if the first 2 are both equal to 1. Okay, so that's this controlled NOT gate here, and then you return C. So that's as you can see, it's a functional program. Okay, written in a functional programming language. And then when you want to AND together a list of bits, then you do the obvious thing. If the list is empty, you return true. If the list is a singleton, you return just Q, which is actually redundant, but for singleton, I didn't really want to return Q and true, so as a sort of slight optimization, we have a singleton, right? And then if you have a longer list, you just AND together the tail of the list, and then you do one more AND with the head of the list, and you return that. So it's functional, okay? It's just writing more or less ordinary functional programs. And then there's a bit of plumbing here. Print generic preview means print this quantum circuit as a graphic and then use the previewer to display it. And list is the function that we want, the quantum circuit that we want to view and replicate 10 qubit is a parameter that tells you, because this function actually would take any list of qubits as an input, but when we want to actually view it, the quantum circuit, we need to pick out a particular member of the family. So here we're picking the circuit with 10 qubits, for example. Okay, so if I run this little program, so you see at the top of the page it says import Quipper, so that's where the embedded language actually lives. And as you will, so let's run this. And ta-da, it generates the quantum circuit for ANDing together 10 bits. It's not the most ingenious circuit for doing this. You could do this with logarithmically many ancillas instead of n, okay? But it's exactly what this program does. And you could write a more clever program if you wanted to. Here we're designing the programming language. We're not trying to write clever programs. Another example is the algorithm for the binary welded tree. That's some kind of walk on a graph. You have a graph with some kind of nodes and they're colored, and you're trying to find the unique node with some property by randomly walking around on this graph. And I just wanted to show it as a quick example, just so you see that relatively large quantum circuits can easily be generated with these functional programs. So here you have some kind of oracle. This is some kind of oracle implementing like some edge, computing whether or not there exists an edge, computing actually the neighbor of a vertex in the graph. Then you do something. Whoops, it's kind of hard to. Let me switch to a better view here. Fit height. Okay, there's no keyboard shortcut for that. Whoops. Yep, here's some kind of oracle. Then there's some kind of step. All these gates are classical. All of them are just controlled NOT gates. You could apply them to ordinary bits. It wouldn't have to be qubits at this point. Then there's a relatively small part of the circuit where it's actually quantum. That's the actual time step. You do a kind of basis change, then another kind of basis change. Then you perform a single quantum gate here, which is actually some kind of tiny rotation about some angle. And then you undo the basis change, and then you undo the whole oracle, and so on. This is sort of how these quantum algorithms work. And okay, so that's the idea of Quipper. You write a functional program, and it generates the circuit for you. Now, what did I do with my slides? I think I have quit my slides. Start up again. All right. Now, but it wasn't type safe, okay? So what we're currently working on is making a sort of type safe redesign of Quipper. Now 5 years have passed, we have a bit more time, the whole project doesn't have to be finished in 6 months. So we want to actually from the bottom up actually design a programming language that does exactly the same thing that Quipper does, but that has some kind of theory, some kind of soundness theorems, and hopefully a denotational semantics, okay? And we call these languages Proto-Quipper. All of the languages that we might develop that are sort of Quipper-like, currently all called Proto-Quipper for prototype Quipper, okay? Okay, so and what I want to tell you about today is we actually have a denotational semantics for Proto-Quipper now, which I think is quite neat. So what is Proto-Quipper? How should we think about it? It's a language for describing families of quantum circuits. Not just a quantum circuit, but a family of quantum circuits. You might want one of the inputs to be a parameter, like the number of bits that this circuit should have, or the number n that you wish to factor if you want to use a quantum computer to factor, okay? Or any other, or any kind of parameter. So when you have a language for describing a family of circuits, this is very similar to a hardware description language. This kind of thing exists, right? Programming languages for specifying hardware. And what all these hardware description languages or circuit description languages have in common is that they have two different runtimes. First, you run the program and it generates the circuit. Then you run the circuit and it generates some output. Okay? And these two levels are separate. You cannot change the circuit after you've already started running it, for example. So that's why there is a distinction between parameter and state. So a parameter is some value that is known at circuit generation time, such as the number of qubits or something like that. And a state is a value that's known when the circuit actually runs, such as the value of an actual qubit in the circuit or a bit in the circuit also, if you have classical circuits. And informally, the state can be a function of the parameters. You can initialize a bit, from a Boolean, but a parameter cannot be a function of the state. And that's basically the essential thing that our denotational semantics has to capture. So I will start with a simple model of parameters and state. And this is very surprising because it's a very simple category theoretical model here. In fact, we have seen this model sort of as a model for other kinds of phenomena, and it's interesting that it works here. So let 2 be a 2-object category. So I mean the category with 2 objects and one non-trivial morphism between them. And there's also 2 identities, so it's a 2-object 3 morphism category. And consider the functor category set to the 2-op. Okay? Every category theorist knows what this is. Most of you are not category theorists, so let's just describe it concretely. An object of this category is a triple consisting of a set and another set and a morphism between them. Like this vertical A here is a morphism, is an object of the category. And then a morphism of the category is just one of the commutative diagrams. Okay? Now, why in the world should this have anything to do with parameters or state or quantum programming languages? We can think of these. So if you have one of these, here's your A1. That's a set, okay? I'm just talking about a set. A0 is a set. Okay, this set A0 has some elements maybe. Set A1 also has some elements. And there's a function between them mapping, these elements to those elements. If one of these elements here is called little x, we think of the elements of the lower set as the parameters. Okay? So here's a parameter little x. That's an element of the set A0. Then above this lives a certain subset of A1, namely just those things that are mapped to A0. Right? So we call this the fiber over x, and we call it A sub x. Okay? And here's another element, y, for example, and then here's the fiber A sub y. Sometimes the fiber can be empty, sometimes it's a singleton, right? Sometimes it has more than one element. So we think of these elements as the parameters, and once a parameter is given, then you have a set of states. Okay? Think of the upstairs things as the states. But the set of states is not just a set, but it's a set of states over x, and another set of states over y, and so on. For example, if the parameter is the length of a list of bits, then if the parameter is 5, then you have 32 elements, which are all the bit lists of length 5. But if the parameter is 6, you have 64 elements, and so on. So we structure. So we have state and parameters, and I have this on the next slide, but without a picture. Okay. So this fiber A sub x, and then the interesting thing is how we think of the morphisms now. So suppose you have another one B. B1, B0, right? Here another bunch of states, and they also have fibers, like B sub Z, okay? Now a morphism is by definition a commutative diagram, so that means, first of all, a morphism is a function f0 from parameters to parameters. And second of all, then we also have a function here f1, from states to states, but it's not arbitrary. the diagram has to commute. And if you think for a second about what it means for the diagram to commute, it just means that any state over x must be mapped to a state over f0x. So you have a map from parameters to parameters, and then for each little x, you have a map from the fiber to the corresponding fiber, so that the state maps must be somehow compatible with the parameter part. And now you can see that, for example, if this point here were being mapped to a point over here in one of these fibers, then you can see that that point is somehow a function of this point, but also of y in a sense. But the point that y maps to is only a function of y. Like if this is f0 of y, f0 of y will be the same thing even if you look at different states. If you vary the state but keep in the same fiber, that does not change f0 of y. And this formalizes this intuition that the parameter is a function of parameters, but state is a function of state and parameters. Okay, so that's basically the whole idea. Now, that's a simple idea. And in fact, this is a well-known model, for example, in security, where you talk about classified and unclassified information, and your policy is that classified information might depend on unclassified information. Like you can read something in a newspaper and then still put it in a classified document, but you cannot read something in a classified document and then put it in a newspaper. So all the unclassified output should only be a function of the unclassified input, but the classified output can be a function of everything. So they use exactly this model actually in that situation, but it's a different interpretation, okay, than what I have in mind. But it's the same model. And surprisingly, we can get relatively far with this simple idea. So here's some examples of object. So bool is, of course, the type of true and false, but viewed as a parameter. So that here I have a two-element set and the identity function. That means there's two Boolean parameters, true and false, and then over each of them the state is, the fiber is just a singleton. So the object bool we can think of as the Booleans that are known at circuit generation times and they have basically only parameter and then trivial state. And conversely, you have bit, which is in some sense also Booleans, but this is Boolean state, things that will be known at circuit runtime. And you have no parameter. A bit has no parameter, but it has two different kind of state. Okay. So the object. So I think on the slide I have, but I didn't say. We say a generalized element of this object is just a pair. It's just a generalized element is just a pair of a parameter and a state, such that A of the state is equal to that parameter. So this object has two generalized elements, namely 0, 0 and 1, 1, which we can identify with false and true. And this object also has two generalized elements, namely star 0 and star 1, if we think star is the unique element of the singleton set here. And we also identify these with false and true. And now it's easy to see that there's a morphism from bool to bit mapping false to false and true to true, but there isn't a morphism from bit to bool mapping false to false and true to true. And that's because this diagram commutes, but you cannot possibly make this diagram commute. This question mark here doesn't actually have a solution. And that this again sort of formalizes the idea that parameters should not be functions of state. Of course, there are functions from bit to bool. There are commutative diagrams, but they're not going to be the identity up here. In fact, the only two existing ones are the two constant functions. Indeed, you can have a constant function, that depends on the state. Okay, so this is not yet a model for quantum circuits. Okay, I didn't have any quantum thing in this model. This is sort of a model for, let's say, let's sort of see what kind of programming language we get in this model, actually. My game is I will first define a model and then I will define the programming language that fits the model. Okay, so what kind of programming language would fit this model here? Well, first of all, it's a Cartesian closed category. So certainly, vanilla simply typed lambda calculus can be immediately interpreted in there with no problems. The category also has coproducts, so I can have sum types, disjoint union types basically. Bool and bit, we've just seen, are objects in this category, so these can be base types. My lambda calculus has a type bool and a type bit. Also, this function init from bool to bit would, for example, be a morphism that can be a constant in my lambda calculus. And I have other things here, for example, constants true and false, and if-then-else construction, as well as built-in gates. A gate would be something like a function from bit cross bit to bit, like which we think of as a gate in a circuit, rather than if it were from bool cross bool to bool, then it's like a if then else in the programming language, but it's from bit cross bit to bit, then we think of it as a gate. Okay? The sort of thing that will be evaluated at circuit runtime rather than circuit generation time. So we have all that. Moreover, the category is co-complete. So we have initial algebras of continuous functors. In other words, we have inductive data types here as well. Natural numbers, lists, trees, all the usual types. So that's quite a rich programming language, actually. And so it's a simple functional programming language for describing families of Boolean circuits. These are ordinary Boolean circuits. So I have bit, I have bool, I don't have qubit, right? But you have gates such as AND, for example. So this describes ordinary circuits, not the reversible kind. And you can actually use this programming language. It's actually quite convenient and type safe, right? Because it has a model. But we want to do, there's more structure in this model even that I haven't talked about yet. There are 5 functors between set and set to the 2 up, and all of them are adjoints to each other in this way. And from these adjunctions, so here's what the functors are. There's an obvious embedding from set where you just take a set and let A0 and A1 both be that same set and take the identity. That kind of thing is called a parameter type, a type that has just parameter and no state. Like bool is an example of something of that shape. Okay. And then it turns out to have both left and right adjoints, and they in turns have left and right adjoints. And of course, this is not a new thing to category theorists. It's true for any pre-sheaf category that you have, such functors. But for us, it's interesting because the fact that these two are an adjunction, for example, gives you a comonad on the model. And that comonad will be the bang of linear logic. We are not going to really use it here because we have sort of classical circuits and we are not worried about linearity. But later, that bang of linear logic will come in handy when we are in a linear setting, and then certain things might be nonlinear. Similarly, the fact that you have an adjunction between these two functors gives you a monad on the object, and that monad also has a computational interpretation. We call it the shape monad, but I will actually sort of skip that monad in the interest of time. So we have interesting stuff. And like I said, the bang kind of course, well, I'm going to skip the bang, okay? Because we're going to get to the bang again later. What I want to do now is do a model of Protopaper. So reversible circuits of some kind or quantum circuits should be synthesized here. Now, my model was very set theoretic, okay? Absolutely, it was Cartesian and so on. It's not clear how you're going to get linear logic really in there in sort of a meaningful way. So when we want to make a model for Protopaper, we should ask at a fundamental level, what is Protopaper? Well, it's a language for describing families of quantum circuits. So what in the world is a quantum circuit? Now I could go and define it, okay, like it's a certain pictorial diagram made up from boxes or whatever. But actually, it's much better to take the abstract point of view and say, a quantum circuit, definition. Let a symmetric monodal category of quantum circuits be given. Okay? A quantum circuit, therefore, is just a morphism of a symmetric monodal category. So the whole language can actually be described at this generality. It doesn't matter what your category of quantum circuits is. It only matters that it's symmetric monodal. So you take your favorite gate set, take quantum circuits over qubits or qtrits, or have bits in there also and measurement or whatever. Whatever you want the gate set to be, that's your monodal category. So Protopaper, the generalized view is that Protopaper is a language for describing families of morphisms in a symmetric monodal category. We no longer even have to talk about quantum, which is nice, I think. Most people don't like quantum mechanics for some reason. They like to think about it, but yeah. Anyway, so we need to keep the best parts of this model that I just described, but we need to make it work with a monoidal category rather than set. Okay, so how do you do that? Turns out this category set to the 2-up has many properties, some of which I already discussed. What is the property that we need to generalize now? It turns out the viewpoint is something a bit surprising. Set to the 2-up, among all the other things that it is also the free coproduct completion of set. Okay. As I think John or someone pointed out, that definition of coproduct completion already has set built into it, because set itself is the free coproduct completion of the one object category. That's exactly what we will generalize. So here's the model on one slide. That's the whole definition. Everything after that will be theorems, okay? More or less. Fix a symmetric monoidal category of M of circuits. This is a concrete category. We imagine that if we had a morphism in this category, we could print it out in some way, okay? Or display it or put it in a data structure. These will be the actual circuits. It may have some distinguished objects such as bit, qubit, qtrit, okay? And maybe some distinguished morphisms called gates. Whatever they are is up to the user of the programming language, but let's say there are some distinguished objects, morphisms called gates. So this is given, okay? Now we're going to construct the model in 2 steps. And then after that, we're going to construct the programming language to fit this model. First, we're going to fully embed M in some arbitrary way in a symmetric monoidal closed category. M is only symmetric monoidal, so it has tensor products, but it doesn't have function spaces, which would be appropriate for circuits, right? But we're going to fully embed it in a symmetric monoidal closed category. That means we add the function, we add the higher order structure. For example, and also we want this category M bar to be product complete as well. This can always be done, for example, by the Yoneda lemma with the day tensor, or you could do it in the free way, or you could do it. The point is, in my model construction, I'm not even going to specify how we're going to do this. I'm just going to specify that we're going to do this. And as a consequence, any theorems that I prove later will be independent of the particular way in which I have done this, which means I will never actually compute anything in a Yoneda category or anything like that. All the theorems will be independent of how you do that. So that's a purely abstract thing. It only exists to support the higher order structure. At the end of the talk, someone will ask, is the model fully abstract? Because everyone feels obliged to ask a question like that. But full abstraction, while it's of great theoretical interest, has no practical application whatsoever. And the proof is, whether or not it's fully abstract depends entirely on how you chose this category M bar. If you choose it freely, then it will be fully abstract. If you choose the Yoneda lemma, it will be manifestly not fully abstract. But the point is the model will be adequate and ground fully abstract, which means anything that we can write down at ground type will be distinguished by the model if and only if it's distinguished in reality. Right? And at higher types, it's the abstract question. Not only do we not answer it, but we manufacture the definition so that that question cannot have an answer. And I think there's actually a point there, so referees beware, right? So that's first what we do. So that's the category of state in a sense. And then we add the parameters by letting M double bar be the free coproduct completion of M bar. Not co-limit, but coproduct completion. What does this concretely mean? The objects of M double bar are going to be families of objects of M bar. Essentially sequences of objects of M bar, but could be indexed by a set rather than just by some natural numbers. So an object concretely is a pair consisting of a set X and then an X-indexed family of objects of the category M bar. So the set X is this, but rather than saying over each element of this X we have a fiber that's a set, we're saying over each X we have a fiber that's an object of the category M bar. The fibers are object of M bar. And then the morphisms are the appropriate thing. So the picture is the same, right? The bottom guy is still an honest to God set, but here I have this A sub X is now an object of the category. It no longer has elements, right? This A sub Y is an object of the category M bar. And a morphism now will be a pair F0 of a morphism between the underlying sets. And then for each X, for each little x, sort of a morphism of the category M bar that's called F sub X, which goes from A sub X to B sub F of X, B sub F0 of X. right? And that's exactly the definition of morphism that's written on the slide. It's the thing that it has to be if you want to follow, what we did before. But this category M double bar has surprisingly many properties. Obviously, it has coproducts because I added them freely. So certainly it will have coproducts, okay? The fact that it's monoidal, the fact that it's symmetric monoidal is also not too surprising because you can sort of imagine the way you define the monoidal structure is completely straightforward, right? You take the Cartesian product of the states, and then for each given pair of states, you take the tensor product of those two parameter spaces over those states. And it's not surprising to me that that gives you a monoidal structure.
In that sense.
So the parameters are the elements of the set X, and the states are virtual, right? They live in the object A sub X, but they're not elements, of course, because that's not a set. But we don't have to talk about states. We're talking about circuits, which are morphisms, right? We think of states as sort of existing, but yeah. So we don't have states, but we have state spaces, okay? The fact that it's symmetric monoidal closed is actually surprising to me, at least. So you have this symmetric monoidal structure is actually closed. Normally when I freely add coproducts to something, I don't expect it to be closed because that's not one of the structures I sort of explicitly preserved. But you can check, there exist these function spaces, and it actually does give you a right adjoint to the tensor product. Moreover, there's an obvious embedding of set in M double bar, which just takes the set X and then the trivial fiber over each element, which is the unit of the tensor. And that functor again has a right adjoint, just like it did before, maybe also surprising. And this adjunction actually forms a linear nonlinear model of intuitionistic linear logic in exactly the sense of Benton 1994. So there's a model of linear logic right here. So, and we don't have co-limits because I only added co-products freely, but it turns out usually you need co-limits to do initial algebras because you want to do 0, arrow f of 0, arrow f of 0, arrow f of 0, and then you're going to take the co-limit of this whole sequence. That's how you construct the initial algebra for the functor f. This category only has co-products, but it turns out that's enough to compute the sort of initial algebras that we're interested in. Namely, if you have functors that are only built from sum and product, then it turns out the co-limit that you have to compute turns out to actually be an infinite co-product. So this, you can actually interpret inductive types in here. For example, list of qubit is a type, is an object in this category. Okay, or list of bit, or even the natural numbers, or trees, or any of these other. So we have quite a lot. So we have Booleans, we have natural numbers. An object is a parameter object if all its state spaces are trivial. We have sort of basic objects for the category M. So these are wire types like bit and qubit. Labeled, objects of the category M correspond to labels on wires. And then we have gates. And it turns out and we have a model of linear logic, okay? And in the model, bang of u arrow t, if u and t are objects of M, then bang of u arrow t is actually a parameter object whose underlying set is exactly the Hom set of u arrow t. So the elements of bang u arrow t, or the closed values of u of that type, are going to be exactly the circuits from u to t. So then we define, so now we have, okay, it's monoidal closed, so we can interpret a standard linear lambda calculus in it with coproducts also. We can have base types like bit, qubit, bool. We have inductive types, and the variables that happen to be of parameter type, of type bang A, can also be duplicated. So even though you have a linear lambda calculus, it's for ordinary lambda calculus for those. You can also have some external operations. Like you saw in my Quipper example, at the end I printed the circuit, for example, and I viewed it in Acrobat Reader. So if you have a function print, which takes you from a Hom set to a set of documents, then that's external to the category M, but it would internally turn into a morphism in my model. So even the print function lives in the model, okay? And then now we make the programming language that basically contains all the stuff I told you. So these are the types. We talked about all these operations. Some types are parameter types, and you can say syntactically what they are. Simple types correspond to objects of the original category M. And a circ corresponds to circuits. Contexts are as usual, judgments are as usual, and the terms and typing rules are as usual because everyone knows what a linear lambda calculus is. Okay. The only thing that's maybe slightly different is for the bang. Bang is a comonad, so you have lift and force. Okay. So that's really sort of as simple as it can be. And of course, when you have parameter types, then they're duplicable, so you can use them in both hypotheses. So ta-da! Now I've made a language to fit this model. Now we also made an operational semantics for this language. I'm done, right? And then it satisfies all the usual theorems. In particular, it's sound. So you have a small step semantics. Each state denotes a morphism of the category. When one state reduces to another state, they denote the same morphism. Therefore, the initial state and the final state denotes the same morphism. Therefore, the operational semantics computes the same circuit as the denotational semantics. So that makes the language sound. And as Gordon pointed out, a sound semantic is automatically adequate. I always forget to say this in my papers. I just prove soundness and forget to say it's adequate. And then later someone else writes a paper saying it was not known to be adequate. And now we've proved it to be adequate. This actually has happened. So the end. Thank you very much.
Going back to your remarks about full abstraction, I'm not disagreeing with your methodology here, but I think you overstated things a bit.
Okay.
As an example of where full abstraction is useful is when people are doing compositional model checking, so you're looking at program fragments. So knowing that the semantics with respect to which you're doing model checking is fully abstract is actually directly used there in showing that your verification applied to the open piece of program is relevant to the sort of observation and behavior in general.
You're absolutely correct. I was being polemical. Of course, there are some good reasons to want to prove full abstraction results in these sort of situations. Yes.
I thought you were, but I thought we'd
However, but often, if you have a model for something and you're not fully abstract at the higher order types, but as long as you're sort of fully abstract at the ground types, for many practical things, that's absolutely all you would ever hope for or even want. So, but of course, there are exceptions. Like when you want to reason about all programs in some, for example, in an adversarial context, like if you have cryptography and you want to reason about all attackers, you think of the attacker as being a morphism in the model.
Also, this compositional point as well.
Yes. So there, yes. Yeah. So take it with a grain of salt, right? What I said.
I don't mean this as a criticism, but I think Feynman once said that a good thing about quantum computing is it'll help us understand quantum mechanics. So you might ask, what's the best choice of M and M bar? But maybe not ask that question. Do different choices of M and M bar give different properties of circuits?
Different choices of M will just give you different classes of circuits. So you can use this same language as a language for describing.
You have a program, right? And so a program would behave in one way under one semantics, but another way under another semantics.
Right, and that's right. The M is sort of like the signature of the language. Usually when you define a language, you say, and then there are some arbitrary base types and constant symbols. For example, you might want to have a language about natural numbers, and then you have one kind of base types and constant symbols. If you want a language about Booleans, you have a different kind of base type and constant symbols. So that's a signature. The M here plays the role of the signature, the given set of gates and types, over which. But the interesting thing is that the rest of the language then works uniformly, as the signature was given.
So the embedding into M bar doesn't make any difference?
The embedding into M bar doesn't make any difference, as long as it's full and faithful. I mean, it doesn't make any difference to the theorems that we prove.
I may have misheard you, but do you rule out D-Wave as doing quantum computing?
I didn't say anything about D-Wave, did I?
I think you mentioned that if they had a quantum computer, the DoD would have locked it up, something along those lines.
If the NSA had a quantum computer that could factor, then they would certainly keep that classified. I don't think the D-wave machine can factor, so whether it's a universal quantum device, I have no opinion about.
I'm not sure I'm going to formulate this question very well, but I'm probably not the first person to ask it, so maybe you can give a perfect answer to the question I should be asking. Right. So in describing this as a language for producing quantum circuits, and I think when you referred to the operational semantics at the end, you were describing the operational semantics of the construction of the circuit. But there's something a little bit different here compared with the way we think about classical programming languages. And so, for example, you showed some very enormous circuits at the beginning. So if you imagined using Quipper to end up actually doing computation, I don't think you're suggesting that Quipper would construct this enormous circuit which you then physically build and feed data through.
It's not. These are not hardware circuits.
Well, this is my question. So, I mean, by analogy with, so say when you define a classical programming language and give it operational semantics, what you're doing here seems to be a bit like saying that the operational semantics of a Java program is the process of constructing an assembly language program that does the same computation.
No. Whenever you have a operational semantics, let's say a call-by-value language, because this is call-by-value, it turns out. For example, you have your big step semantics, which somehow evaluates your program to a value, and we consider for it sort of observable to be values of ground type. Like, for example, bool. In many languages, you just take bools or integers to be the final out. You have all your higher order programs and so on, but at the end of the day, you compare like whether two programs compute the same Boolean. So here what the point of view is that a circuit is an observable. So the circuit is the thing that you're actually computing. The circuit itself is just a list of gates, and the list of gates is of course not hardware, but it's something you would pass as a set of instructions, say, to a quantum computer. So yeah, that is what it computes, right? This is the difference between Quipper and the quantum lambda calculus. The quantum lambda calculus is also a higher order language for quantum computing, but we imagine it running sort of directly on the quantum computer or with access to the quantum computer. So when you do a measurement in the language, the measurement will be done. When you apply a gate in the language, the gate will be applied. But in fact, it turns out one thing, when you want to actually implement quantum algorithms that are non-trivial, there's a lot of meta operations. In the research paper, it might say, it is well known that such and such program can be solved in polynomial time. Therefore, there exists a Boolean circuit for it. Now use the standard trick to make this Boolean circuit reversible. Then, turn it into a quantum circuit. Then apply amplitude amplification, which is another sort of strategy that takes a circuit and produces another circuit. So it turns out for all these higher operations, you want to treat the circuits actually as data. Not just as something that you do on a quantum computer, but the circuit itself is constructed and then modified. So this you can do, and this is sort of the whole philosophy of Quipper. For example, you have constructed a circuit and now you would like to decompose it into a different set of elementary gates. Typically what you can do in Quipper-like languages.
Okay, I think we need to move on. Thank you very much again.